detailed.
Yeah.
Very smart young researcher got a permanent position last year. And we prepare this because usually people arrive late, so no matter when you start. You need a pointer?
I was thinking that, but maybe I can use here.
Well, I know that Martina who's the technician, prefers this because on streaming they will not be able to see the pointer.
Yeah.
While they
so
see
I
this
can
one,
do-
but I can ask.
No, don't worry. I can use
I
it.
want a normal one. I have to buy one, but I'm so lazy. So sure, otherwise I just run.
No, I'm really okay with it.
She will bring a pointer, a laser pointer, so then you can decide. I think we can get started also because then you have your secret meeting with the secretary.
Yeah, I was thinking that then 12:30. Sorry, how to boost also my tone.
Don't worry.
And then we have to
start. Welcome everybody. It's a pleasure to me to welcome Celeste Artale, today's speaker. Celeste studied in Buenos Aires where she got her PhD. Then she became a postdoctoral fellow in Argentina and she moved to Innsbruck where she is now as an independent postdoctoral fellow. She is a FWF, postdoctoral fellow, which means basically National Science Foundation, Austrian National Science Foundation postdoc, working on an independent project, on an independent grant. She is basically a cosmologist. She has worked with cosmological simulations for her entire life. And now she combines her first love, cosmological simulation, with the study of binary compact objects. And she's going to talk about host galaxies of merging compact objects.
Okay, thanks, Michela. So hello, everyone. Thanks for coming to my talk. So, as Michela said, I would like to talk about the host galaxies of merging compact objects. This work is in collaboration with excellent researchers, collaborators from here, from Innsbruck, from Trieste also. And first, before talking about science, I would like to make a short acknowledgement because maybe, I don't know if you know, but there is a partnership between the University of Innsbruck and this one is? Okay, thanks. Between the University of Innsbruck and the University of Padova. And well, this time I came here several times now, but this time my visit was funded through this partnership. So in case you are interested, and begin new collaborations in the future, these are very nice pictures of Innsbruck. It's a very nice city between the mountains, between the Alps. So now let's go to science. First, I would like to give you an outline of my talk. I will try to convince or tell you what can we learn from gravitational waves observations. Then I will try to convince you why the host galaxies are so important to study. And I will present some of my results, the methodology, and finally I will give you my conclusions. Okay, so let's go to the introduction. As you know, the frequency of the gravitational waves is super large, let's say. And so we have in the, let's go with this. On the left extreme, frequency is about 10 to the minus 16 hertz. that are produced by the cosmic micro background. And on the, here in this plot, the frequencies of about 10 to the 2 hertz are mainly produced by binary neutron stars and binary black holes and black holes neutron star merging compact objects, which are basically those that can be detected through ground-based interferometers, like in the case of LIGO-Virgo detector. So my talk will be focused on this part, on these gravitational waves produced by merging compact objects. So I think that you may know that so far from the runs 1 and 2 from the advanced LIGO-Virgo detectors, they have detected in total 10 binary black holes and one binary neutron star that can be seen in this nice plot here on the right panel. So the blue circles corresponds to the detection, so the scheme where you can see the masses of the black holes that were detected with LIGO-Virgo from LIGO-Virgo collaboration, and in the violet purple circles corresponds to the black holes detected or that are within X-ray binary, so detected through electromagnetic measurements. So you can see here that there is a kind of shift or discrepancy, let's call it, between the masses of the X-ray binaries detected with the masses of the black holes detected through gravitational waves. So this is one of the open questions. And here you can see the yellow dots are the masses of the neutron star detected through with electromagnetic detections, and here from LIGO-Virgo detector. So, and also there is a big debate about this mass gap, but now let's keep. And as you may know, now we are the LIGO-Virgo is ongoing on the 3rd run, and so far till now, I think we have 4 likely binary black hole mergers, 1 double neutron star, and probably the first, I don't know, maybe the first black hole neutron star detected. Okay, so here I would like to give you my thoughts about why gravitational wave detections are super interesting and help open a new era for astronomy, and in which aspects the gravitational wave detections can help us to understand many exciting open questions in astronomy. So this will be my thoughts. Okay, one of the very interesting aspects is that the gravitational waves can help us to study different stages of stellar evolution that are under debate. And here on the left plot, left plot that you see here, you have a scheme of the evolution of 2 massive stars that underwent to a double neutron star merger, and all the processes behind to reach this stage. And there are, in particular, some uncertainties about this evolution. For instance, in the common envelope evolution, also in the momentum kicks imparted by the newborn neutron stars, and also the mass distribution of neutron stars. So studying the properties of the gravitational waves could help with all these open questions. Besides that, also gravitational waves can help us to study the mass spectrum of merging compact objects. Here I show one, because this is something that's still under debate also from population synthesis models and stellar evolution models. Here this is some results from Spera and collaborators 2015. This is the remnant mass of the compact object as a function of 0 age main sequence mass, and these were holes of in the same range that the black holes detected by LIGO-Virgo collaboration. And another aspect that I put in this slide that is super interesting is where gravitational wave can help, of course, is to study and disentangle between the different formation channels of merging compact objects, which are basically the two main possibilities are the isolated stellar binaries, and also they can be formed dynamically in dense environments, such in globular clusters. Okay, another aspect that can be where we can use the gravitational wave detections is to discuss first the nature of the dark matter, which, as you know, we still haven't detected yet. But there is a hint that primordial black holes might be a fraction of this dark matter. So this is one point. And on the other hand, gravitational waves can be used as standard sirens to measure the Hubble constants. As you know, the universe is expanding, and the Hubble constant can help. It's a measurement of the velocity of the expansion locally. And so there are different ways to measure the Hubble constants, as you know. One is, for instance, with the cosmic microwave background with Planck, also through the standard rules, through the supernova 1A. And there is a dichotomy of the difference between the values reported by the obtained from Planck collaboration and obtained from the supernova or the standard candles. So gravitational waves can be also super useful for this because they are standard sirens. So having the distance of to the gravitational wave plus the redshift, if we can detect the host galaxy, we can measure also or have a new measurement of the Hubble constant, which is something that I show you here with only, well, so far one detection, that is the double neutron star detected, GW170817. So, and this is the value that they reported here. Okay, so I think that I tried with this to convince that gravitational waves are super useful for many open questions in astronomy. But another aspect that is very important is the localization on the sky of the gravitational waves. And here on the left panel, you see it's a scheme of the localization on the sky of many of the gravitational waves reported by LIGO-Virgo collaboration. And you see that the distribution of the localization are super wide. So if we can know something about where is, and we have in this region, we have lots of galaxies, but on the background. But what we could do is, for instance, studying or learning if there are more galaxies in this background that are where it's more likely to find these gravitational waves. So knowing more about which are, for instance, the host galaxies where it's more likely to detect the gravitational waves can help us also with to localize or reduce the area on the sky. On the right panel here, this is for the first double neutron star detected. You see here different shaded areas that corresponds to different reports from Fermi, from the different detectors that study the double neutron stars, the merging double star. And so, as I told you, Before this was the first one, and after the detection of the gravitational wave, a short gamma ray burst and a kilonova was detected. And so now we know exactly the host galaxy of this gravitational wave, which we name as LGG 9443. Yeah, okay. It's okay. Is it 90? Yeah, confused. 4993. Sorry. Now that I read here, yeah. And so it's a massive galaxy. It's an early type galaxy, and the star formation was taking place. The most of its star formation was taking place about 11 giga-years ago. So it's not. It's a star that is not forming a big amount of. It's a galaxy that is not forming a big amount of stars at this moment. So there is here a problem with that, because basically the models, previous reports, previous models, says that double neutron stars might be formed in star-forming regions. Hence, they might be formed in late type galaxies, in galaxies that are forming stars now. So I will put this like a question, and then I would like to convince you that no, this is really the place where we are expecting to find a double neutron star, emerging compact object, emerging double neutron star. Okay, so some other interesting results that where we can use the host galaxies to study emerging compact objects is, for instance, this from Mapelli Giacobbo 2018, where they investigate the stellar masses of the galaxies where the different merging compact objects merge and form. Here on this plot, you see here, yeah. The red lines corresponds to the distribution of the stellar masses of the host galaxies where the merging compact objects merge, while the black dot lines corresponds to the distribution where the merging compact objects form. What I mean is when the stars, the binary stars form. And you can see here that in the case of the double neutron stars, the host galaxies where they form and where they merge are massive and are similar. The distributions are similar. Compare with, and if we compare with double black holes and black hole neutron stars, you see that they form in low mass galaxies while they merge in massive galaxies, about 10 to the 11 solar mass. How we can understand this difference between the masses of the host galaxies? Well, here on the right panel you have the delay time distribution. The delay time is the time between the moment where the binary system, stellar system form, and the time where the emerging compact object merge. And what you can, so let's forget these thin lines here, just the thick lines, see here. And you can see that the distribution for double neutron stars is peaked at very low values for delay time, which means that the emerging compact objects from double neutron stars merge and form in environments, in super similar environments. So that's the reason we find here that the masses of the host galaxies are mostly the same for the formation and the merger of the double neutron star. Differently with what we can find for the double black holes and black hole neutron star, which is the delay time is peaked at higher values. And this explains is different since the formation and evolution of galaxies as times across cosmic time, what happened is that the masses of the galaxies increase. So that's what we find here. Also, from this paper from Safarsa, Det, and Berger, that was years, some weeks ago, we see that the host galaxies, studying the host galaxies of merging compact objects, can also help us to investigate the delay time distribution of merging compact objects. So, in these plots, in this work, what we did is computing on exploring how many host galaxies we should detect to constrain the parameters of the delay time distribution for double neutron stars. And well, they claim that they should need about 1,000 galaxies to constrain the parameters. So, saying all this, I hope I convince you that host galaxies are super interesting. Host galaxies of merging compact objects are super interesting to study, and they can help us for many things. So I'll go now to our results and to the methodology that we implemented in our work. So for that, what we did is using the results, the galaxy catalogs from the hydrodynamical cosmological simulations, and combine these galaxy catalogs with the catalogs from population synthesis models. As you can imagine, the scales are completely different, so we have to combine, let's say, very large scale things in terms of galaxies with what is happening inside the galaxy with the evolution of these binary compact objects. For that, what we implemented was Monte Carlo code. We populate the galaxies, the simulated galaxies, with merging compact objects. And with that, we can do a lot of things. We can study the merger rate, cosmic merger rates. We can investigate the merger rate per galaxy, link with the properties of the galaxies, and do this across cosmic time. So this is a very powerful methodology. And well, in this case, I will show just what we are doing now, but we expect to explore many more things with this methodology. So let's go with this video. So here, just a summary about the Eagle simulation, this cosmological hydrodynamical simulation I used in this work. As maybe you know, here first I would like to show you the video is showing different, so gas, dark matter at different stages. So you see here redshift and the size of the length of the video, what it represents. And this, of course, again, for this hydro simulation, is very difficult to deal with physical processes behind galaxy formation, since there are things happening in atomic resolution, also at large scale. So what they do in general is produce these subgrid models to account for star formation, chemical evolution, radiative cooling, AGN feedback, stellar feedback. So all these recipes are included, and they evolve across cosmic time and investigate the evolution of galaxies. So we can use and identify the galaxies at different stages, at different redshift. The population synthesis used in this work is MOPSE, which is an updated version based on BSC code. This population synthesis model includes new prescription equation for metal-dependent stellar winds, new prescription for core collapse supernova, electrocapture supernova, peri-instability supernova, pulsation peri-instability supernova, and it's a very well updated code. Here you see also the mass spectrum. So it's the mass of the remnant. It's a function of the 0H main sequence mass for different metallicities for this code. And as I told you, we have the different catalogs for different metallicities, and according to the metallicities of the stellar particles in our galaxy catalogs, we can match and populate the galaxy with these merging compact objects. Okay, so in this part now, I will show you my results. I will focus basically in this work we focus on in the local universe, so let's call local universe to redshift below to 0.1. Okay, and so here I show you the mass metallicity relation for double neutron stars, double black holes, black hole neutron stars. You can see as expected that as the stellar mass increase in the galaxies, the metallicity of the galaxies increase. And the color code that is represented in each of these panels is the merger rate per galaxy that I will mention several times now. That is the number of compact object mergers per galaxy per unit time. And from here you can see that in all the cases, in double neutron star, double black hole, and black hole neutron star, the merger rate per galaxy is higher in the massive galaxies than compared with the low mass galaxies. And here I will show for the first time, and then you will see several times, the data available for, again I put it in the wrong way, right? Yeah, okay. So you see that the host galaxy of the double neutron star it's a massive galaxy, as I told you before, and as a massive galaxy has a higher merger rate per galaxy compared with low mass galaxies. So let's continue with this comparison now. Okay, so saying that, we also explore the merger rate per galaxy as a function of stellar mass, which is shown here for the different merging compact objects. And so I show the fits here in each case. And what you can find, you find also here is that massive galaxies have a much higher merger rate than low mass, merger rate per galaxy than low stellar mass galaxies. The color code in this case is the metallicity, and another aspect that is super interesting to see is that this relationship is much steeper in the case of double neutron star than for double black holes and black hole neutron stars, showing that the dependence with the stellar mass it's much more important for double neutron stars than for the other merging compact objects. Okay, we can also see this in terms of the merger rate per galaxy, or the efficiency of the merger rate per galaxy, computing the merger rate divided by the stellar mass, which is what I show here. And what we found is that basically, and mainly in the case for double black holes and black hole neutron stars, is that low mass galaxies are more efficient for merging compact objects than high mass galaxies. This is also another interesting aspect reported previously. Okay, so we know now that the stellar mass of the galaxies is a very it's an important property to know the merger rate per galaxy. So massive galaxies are the most likely place to detect a merging compact object. So let's explore also with, for instance, the star formation rate of the galaxies. And here you have again the merger rate per galaxy as a function of the star formation rate of the galaxies. And you see that the galaxies with a high star formation rate have a higher merger rate per galaxy. in all the cases, also for the double neutron stars. But you can see from here also that the color code in this case is the metallicity, and you see that the metallicity, so galaxies with higher metallicity have a higher merger rate per galaxy than metal-poor galaxies at a fixed star formation rate. But this is something that can be a little bit confused, but if you see in these plots here, let's go, for instance, to this plot here, where we have star formation rate, stellar mass of the galaxies, and the merger rate per galaxy, and the color code is the metallicity. You see, for instance, that for a fixed star formation rate, there is a spread range, it's a wide range of stellar masses. And basically, those, the massive galaxies at a fixed star formation rate are also those with a higher metallicity. So what I'm trying to say is that what we find here in terms of the difference in the merger rate according to the metallicity of the galaxies is a hint or a trend due to the mass of the stellar mass of the galaxy, which is basically the most important constraint for the merger rates per galaxy. On the right panel, you have basically the same that is projected on the left here. So it's the star formation rate of the galaxies as a function of the stellar mass. And the color code here is the merger rate per galaxies. And again, I show here the host galaxy of the double neutron star detected. And you can see that, again, the host galaxy it's in the most likely place where the merging rate per galaxy is much more higher than in the case of mass, the low mass, and low star formation. I would like to make just a comment on this. The star formation rate that we included in this plot is considering that we are covering the galaxies or using the galaxies from the galaxy catalogs with redshift below to 0.1. So it was like recompute using the observational data reported by IM and other papers also. Well, so you know also that the stellar mass and the star formation rate can be also analyzed through the color magnitude diagram. So what we did for in the case of the host galaxies or double neutron star was to investigate the color magnitude diagram of our simulated sample and contrast again with the host galaxy of the double neutron star reported by LIGO-Virgo collaboration. And from here again you can see that for brighter galaxies have a higher merger rate per galaxy, and this seems to be independent of the color of the galaxies. As you know, red galaxies are here and blue galaxies are here, so we also find that the reported host galaxy of GW170817 is in the most likely place to find the gravitational wave. So in summary with this, what I'm trying to say, what I would like to convince you is that, okay, we have this value, this host galaxy that was reported, but this galaxy is in the places that our models claim that is more likely to detect, more probable to detect a merging compact object, a double neutron star merging compact object. Okay, so also we can split our galaxy sample according to the specific star formation rate, or according to also if they are early type or late-type galaxies, since we know that the detected host galaxy is an early-type galaxy, and explore this also in terms of these two different galaxy populations. And it turns out that if we combine, considering that most of the stellar mass in the local universe is located in early-type galaxies, and considering also our results, we found that the local merger rate density for early-type galaxies, in all the cases, is much higher than for late-type galaxies. Again, showing that early-type galaxies are the most likely kind of galaxies or type of galaxies where we can detect gravitational waves, merging compact objects. Finally, another one. But another thing that we can do is explore the delay times of the different merging compact objects split by late-type galaxies and early-type galaxies. And I think that the most interesting, or in my opinion, one of the most interesting results here is for the double neutron stars, because you can see that, okay, there is a peak for short delay times, but in the case of early-type galaxies, the distribution is much wider, so we have a big amount of double neutron stars with long delay times in early-type galaxies, as expected. We can, explore the differences for double black holes, also for black hole neutron stars. And basically, you can see that the delay time distributions are different for these two different galaxy samples. Okay, so now knowing all this dependence with the stellar mass and with the star formation rate, our next step is to explore or provide some hints, some results for people from LIGO-Virgo collaboration now about where is more likely to detect a merging compact object. And for that, now we are studying the joint probability distribution between the stellar mass and the star formation rate across cosmic time, and exploring if the properties in terms of stellar mass and star formation rate of the host galaxies are different at different redshifts. And here, just to give you an idea of our preliminary results, this is for double neutron stars at redshift 0.1 and redshift 0.2. And you can see that there is a shift for the range of the star formation rate of the galaxies to higher values in the case at redshift 2. And this is basically due to the evolution of the cosmic star formation rate in the universe. Also here you can find that the regions where it's more likely to detect a merging double neutron star is for high stellar mass galaxies. So finally, my conclusions. I would like to remark here, there's a lot of things I'm showing, but I would like to remark, like a taking home message is that, the stellar mass of the galaxies is super important. We have shown that early type galaxies are the most likely places to detect merging double neutron stars in the local universe. And that's all. And also that this methodology will provide an excellent tool to identify which are the galaxies that where merging compact objects are more likely to be detected in the future also. Thank you.
So thanks, Celeste. Questions for Celeste? comments? Yeah, Enrico,
I
please.
have a question. How is I'm trying to figure out what is the metallicity influence. Because if the delay time for merging, especially for black hole, is so long, basically all the galaxies were mature when they formed. So
Yes.
why there should be an effect today?
What should be effect today? The metallicity. I don't know if I understand well your question.
Well, you already answered in your paper, is the Manucci relation.
In that sense, okay. No, maybe I confused what you commented, but
So just to see if we understood the question, Enrico says, okay, you have maybe a huge dependence on metallicity in the formation galaxy because black holes form mostly metal poor galaxies. But since they have such a long delay time, the metallicity of the galaxy where they merge has retained no information on the metallicity of the progenitor. So how is it possible that you still get a trend with the metallicity?
Okay, so, but this is because of, it's Manucci relation, so you know that, you know that there is a relationship between the stellar mass of the galaxy, star formation rate, and metallicity. So in our case, as I said before, as time evolves, the galaxy increases their stellar mass.
Is a tracer of the mass of the galaxy.
Yeah, exactly.
It's a
Increases
collateral
the
effect
mass.
of mass. The stellar mass is the only thing in the end that
it's not influencing.
Yeah.
It may be that even the star formation rate is just a side effect. Even the star formation rate dependency of the merging host galaxy is a side effect of mass. So it seems pretty straightforward that the stellar mass is the most important rate.
Mm-hmm. Yeah.
And actually, if I may comment on your question, it's not completely true that at high redshift all galaxies are metal poor.
No,
it's quite
but in general,
downsizing tells us that you can have pretty fast enrichment in the larger galaxies. So you already have quite high metallicity in the larger galaxies.
It's the same effect.
Yeah.
If you had you build a lot of stars long ago, it's better than build stars now because you have a way to get the merging. So it's the same effect. You want to have many stars to start with.
Yeah.
What is produced after that, you don't really care. I mean, it produces something, but it doesn't have any effect on the merging.
Yes and no. Maybe we can discuss it later with other plots.
Yeah.
Or you want to go?
No, nothing particular. But.
Can I ask you where the star formation rate of NGC 4993 is estimated from? It looked like quite an inert galaxy, and especially the place where the kilonova came up. So that is 0.5 solar masses per year seems a bit high. So how was it?
Yeah, well, basically I used the data provided by, I think that is Blanchard, the paper from Blanchard, 2017. And they use a model to study
that's
the
current star formation. Right now. So
Yes. Basically
Integrated.
I integrated. Using the
this is over the last decade.
Yeah, exactly. Yeah.
So
Yeah, because nowadays it's 10 to the minus 2.
Yeah, it's much lower. Yeah, it's 10 to the minus 2, exactly. So this what I try to do is include that we are using galaxies with redshift below to 0.1, so include the...
Maybe, yeah. This is a good comment because maybe we should also clarify in the caption.
On the, yeah, true, yeah.
So, other comments, question? If not, Celeste will be staying here for today and tomorrow. This afternoon you can find her in my office, which by the way is next door to this room, so pretty easy to find. And we hope she will visit us more times in the future. So if you want to talk to her, you can find her pretty easy. Or you can go to Innsbruck using this very nice grant, travel grant, which seems to be harder to get than expected. Okay. So let's thank Celeste again. So you're not the only dyslexic here. The name of the galaxy changes many times, Celeste.
Sorry.
These are sloppy things can...
No, it was super stupid, but...
Yeah, because sometimes in the same slide there was the old name, the wrong name.
No.
No, don't worry.
No, sorry, I think I was trying to understand if there was something hidden for formation of the pair. So, for instance, since when the metallicity is high, you have higher mass loss than your black hole.
Of course.
But it seems that it's a second order effect together.
It's a very good question.
This is something, instead, you have an effect of metallicity related to the fact that the massive galaxies today are also metal-rich.
Yes.
Yeah.
But not that they have an influence on the formation of the pair. That's that I was
Definitely
trying to
not,
understand.
because for black holes with this
Because I thought that maybe in the population synthesis model they have these things inside, and
Yeah, definitely.
But you use the metallicity at the time that the
of course, and they say so
it's
that
not-
probably doesn't have an effect.
Yeah.
Because in principle one can think if the delay time is short, you may create different type of binary depending on the
On when they
metallicity.
form, yeah, definitely.
That
definitely.
was what they're trying to
Yeah.
Here, basically, for black holes, models suggest that the efficiency of formation of these binaries is much, much higher at low metallicity. With this model is 1,000 times higher efficiency at low metallicity. With other models, it can be more 100 of times, but this is huge. So basically, with the black holes, you are completely dominated by
the one.
binaries that form in metal poor environment.
So that forms
But they,
basically at the end it forms solid.
or even nowadays, but only from the metal poor component of the galaxies anyway.
Yeah, because
Yes, but since
Mostly
then the delay time is long, we will not see this now. We will see this I don't know, in another time.
Yeah, here it also depends on the definition of delay time, because what the delay time that she showed are integrated over all the populations.